6:47, it's Wise Guy Wednesday. Today we're getting a crash course in the physics of collisions.
Joining us live from his lab this morning is the Wise Guy, Matt Sellen. Hi, Matt.
Hi, Jennifer. Hi, Matt. How are you guys this morning?
Good.
Good.
It's really great to be back. It's been a month. Did you know that?
We had not realized, but we are glad you are back.
I've been counting the weeks. I went to Florida for spring break. Do you like my T-shirt? I went to the Kennedy Space Center. I'm very proud of my
You know
Apollo
about
shirt.
all this space stuff we're talking about. Matt, what's going on this morning?
Well, we're talking about collisions today, and I want to discuss two different kinds of collisions, or two categories. The first kind we're going to do is where things stick together after they collide, and the second one is going to be where they bounce off each other. And to understand collisions, you have to understand a concept called momentum. And you can think of momentum as oomph, okay? And the way you get a lot of oomph, if you're a football player, is you have a big mass and you run very, very fast. And so momentum of an object is the product of its mass and its velocity. And it turns out that before and after any collision, momentum will tend to stay the same. So what I have here is an air track, which just means that these little cars can move without any friction. So we can say that momentum stays the same. And I'm going to take this car, which has the same mass as the other one. I'm going to collide it into the one that's stationary, and you'll see that after they collide, they're moving with about half the speed. Okay, so this one was moving pretty fast before the collision. After the collision, they're moving a lot slower. And that's because momentum is conserved. This one has half as much mass as both of them do together. That means that before, it's got to move twice as fast so that the product of the velocity and the mass is the same afterwards. And the interesting thing is, if you have a heavy something running into something that's much lighter, which I just did by taking the masses off this one, what happens is it doesn't slow down as much. Okay, so if you have a truck running into a car, for example, the truck doesn't really notice that the car was there, or not quite as much as the other way around. Now, the same thing can be applied, the same principle to things that blow apart. So what I have here is I have a mousetrap with a pool ball on top of it, and I'm going to cut the string with a match. This thing is going to fling the ball that way, and you're going to see the cart go the other way. And this might be reminiscent of Newton's third law that we did a little while ago, but now we can understand this in terms of momentum. Beforehand, before this thing was moving, it had no momentum at all because nothing was moving. Afterwards, the ball was thrown that way, and this thing had to go the other way. It's like when you shoot a rifle, there's a recoil in the opposite direction of the way the bullet goes. And finally, let me just show you, by walking over to this thing over here, what happens if you have something that's very light running into something that's very heavy. Not very much at all. That's like a bug hitting a windshield of a car. Whereas if you have something heavy running into something very light, the heavy one hardly notices the light one. This still is because of this concept of momentum conservation. And I'll talk about some other interesting collisions when we get back.
And so I guess, Matt, that's kind of why some people were concerned about SUVs at one point, the size of them versus smaller cars.
Right.
Yes.
Well, you're safer in a big heavy car than in a little light car, because in a collision, the big car doesn't change its velocity as much as the little one.
Good
Makes
stuff.
a lot of sense.
I did miss you, Matt. We're glad you're back. Thank you. We'll see you in a
Thanks,
few
Matt.
minutes.
We're enjoying